Just another worked example on objects which are connected together. I'm just using question 7 from page 48 of your textbook. And the reason we're looking at this example is because this one involves friction acting, so it's a more realistic scenario. So this is from page 48. So we're told that a car pulling along the caravan gives you the mass of both the car and the caravan. It tells you that there's friction acting on the car, and then there's a separate frictional force acting on the caravan. Okay, the engine force to the left here, as we've drawn it, is what obviously pulls the system along. So it tells us that the full system accelerates at 2 meters per second squared. Okay, so that is the force, or the forces involved in the whole system. So it's like you've got this engine force to the left, and you've got 700 newtons in total of friction acting against the motion. So part A of the problem, we're going to use the full system. Okay, so we just assume car and caravan connected together, and we look at all the forces involved on the full system. So we'll just go through the working for part A to show how we would calculate the force exerted by the engine to pull the car and caravan along. Okay, so applying Newton's second law, because the system is accelerating, as it tells us in the question, 2 meters per second squared. So total mass is 2,200 kilograms, acceleration is 2 meters per second squared, so the unbalanced force acting on the system is 4,400 newtons. However, that's not the value for the engine force, because the engine force is acting to the left. You've got 700 newtons of friction acting to the right in total. This unbalanced force is actually the difference between these two. Okay, so you've got an applied force, the engine force, frictional force is acting against it. When you take the 700 newtons away from the engine force, it will give you this unbalanced force. So that's why we write the formula as Fun equals m times a, because what we calculate here is the unbalanced force. So basically that means that the engine force would have to be 700 newtons greater than the unbalanced force, so that when you then subtract the 700 newtons from it, it will give you 4,400 newtons. And we can write that out just as a wee solution. So you can have the unbalanced force will be equal to the engine force take away 700 newtons, which means we then need to add 700 newtons to both sides to get that 700 to cancel, and that will give us the engine force. Okay, so engine force is equal to 4400 plus 700, and we'll just put that in there. So it's 5,100 newtons would be the force that the engine would have to exert. So likewise, when we're completing part B here, to calculate the force exerted by the car on the caravan to pull it along, we'll have to take account of the frictional force that's acting, but just on the caravan this time. Okay, and so that means that we are trying to work out, in terms of forces, we're trying to work out this tension force which acts in the coupling between the car and the caravan. So, okay, so remember, car exerts force on caravan, but you'll also have tension force acting on the car, pulling it back the way. Okay, because it's an action-reaction force. But we're just going to try and work out the tension force that's required to pull the caravan along. Okay, because we know its acceleration, we know its mass, and we also know this other frictional force that's acting on it. So we'll just go through the working for part B. So again, it's Newton's second law that we're applying, but this time just to the caravan. Okay, so we're separating out the car from a diagram, and we're just looking at the forces involved in acting on the caravan. So you've got this tension force to the left, the frictional force to the right. We're applying Newton's second law because we know the whole system's accelerating, so we work out the unbalanced force acting on the caravan alone. Okay, so mass times acceleration, 1,000 multiplied by 2, so the unbalanced force is 2,000 newtons. But again, what we're trying to calculate here is the tension force which is pulling the caravan along. So this tension force here would have to be 500 newtons greater than the unbalanced force. to then provide an unbalanced force of 2000 newtons, okay, if that makes sense. So that means that the unbalanced force is actually equal to, sorry, the tension force is equal to 2000 newtons plus the frictional force of 500. Okay, so it'll be 2500 newtons. And when you go back to your diagram, you can then hopefully see that if you've got 2500 newtons of tension to the left and you have 500 newtons of frictional forces on the caravan acting to the right, when we subtract the frictional forces from the tension force, that's 2500, take away 500 gives us an unbalanced force of 2000 newtons, which is what Newton's second law is telling us that the unbalanced force will be, okay, from our calculation. Just to mention part C here, we have to work out the engine force again and the tension in the tow bar acting on the caravan when the car is no longer accelerating but is travelling at a constant speed. So in this situation we would then be applying Newton's first law, which is saying that the forces acting on the objects would have to be balanced. Okay, so for the engine force, again, take the whole system, car and caravan. If it's moving at a constant speed, it would mean that the engine force would have to balance the frictional forces that are acting. So the engine force would be 700 newtons, if that makes sense. You've got 700 newtons to the left, a total of 700 newtons to the right, and that would be balanced forces, which means Newton's first law applies and the car and caravan will move at a constant speed. Likewise, in the coupling between the car and caravan, if we want to work out what would be happening there, we'd apply Newton's first law just to the caravan. So we've got this tension force, which has to balance out the frictional force, so the tension in the coupling then in the tow bar would be 500 newtons, okay, because it has to balance the friction to keep the caravan moving at a constant speed. Okay, in part D, the last part here, it says that the car and caravan system now decelerate, and so we have to calculate the force exerted by the brakes, assuming that the other frictional forces remain constant. Okay, there'll be a wee bit of work into that and we'll just go through that just now. Okay, so this is the start of the working for part D. So the acceleration, well, it's a deceleration because the car and caravan are now slowing down because the brakes have been applied, and we're trying to calculate what the braking force here would be. So the acceleration I'm going to put as minus 5 meters per second squared. Okay, previously it was 2 meters per second squared. That was when it was accelerating to the right, sorry, to the left. If it's a braking force that's now applied along with the frictional forces that were applied before, then it means that we've got an acceleration which is acting this way, so it's minus 5 meters per second squared. Okay, because what we had implied in the first part of the problem is that any vectors to the left are positive vectors. Okay, so if we've got an acceleration which is now acting to the right because it's been caused by the braking force, and any acceleration will act in the same direction as the unbalanced force that's causing it, and all the forces here are now going to the right, so it means we'll have a negative acceleration, okay, and that just means a deceleration for the car and caravan. So so we apply Newton's second law, so F equals m times a. This is to find the unbalanced force, and remember, so it's the full system that we're looking at together, because we're trying to find the unbalanced force acting on the full system to cause it to slow down, to decelerate. So that gives us a negative unbalanced force, which means obviously the unbalanced force is acting to the right, okay, because left vectors were positive, so the unbalanced force as a vector is acting to the right, so it's negative. But remember, this unbalanced force is composed of both the braking force but also the two frictional components as well, which total to give you 700 newtons. Okay. So last wee bit of working then. If the unbalanced force should be equal to the braking force take away 700. Okay. Now that's because these two vectors are actually negative vectors as well, so that's why I've subtracted the 700. Okay, because it's two vectors which are acting to the right, so they were already negative. That's why we subtracted them in the first part of the problem as well, because they were acting to the right, which is the negative direction. So you still have to subtract the 700. Okay, and that should give us, so we've got minus 1, 11,000. So basically now we need to add 700 to both sides, and that will give us the braking force. Swap the two sides, and that gives us minus 10,300 newtons. Okay, so that's your braking force, and of course it's a negative because it's acting to the right. Okay, so that means that if the braking force was acting on its own, you would have your unbalanced force would be minus 10,300, but you've got an extra 700 newtons acting to the right, so you still subtract it because it's a negative, and that gives you a total unbalanced force of minus 11,000 newtons, okay, which is what Newton's second law told us it would be from our calculation here using the Newton's second law formula. Okay, so that's a fairly involved worked example when you have not only friction acting right across this worked example, but also when you had a change in the situation. So we went from an acceleration to then moving at a constant speed to then looking at the situation where the system is decelerating.